All right, so flattened data. First things first, who's this guy up on stage? I'm the token IBM rep this year, Karl Taylor. I've been with the J9 VM since basically day one. I've done a lot of things there. Currently I'm the GC guy, but why am I here? Well, for a couple of years I worked on the packed objects stuff. I was the tech lead on that, so some of you are probably familiar with that. And a lot of what I'm going to talk about up here today, and then John's going to follow on with, is sort of what we learned as a result of that. Not so much the technology, but the attitude. So, someone dug up this quote for me. I really like it. And it's much more interesting than, this slide. All right, so, always starts off simple, right? Someone has a good idea. Wouldn't it be better if Java could do blank? And then somebody else says, well, I've got this use case that kind of sucks. And someone else has a different use case. Then you get all the performance guys. Oh, man, if only we could do. And then, of course, you get the future-proofing crowd. And pretty soon, you've got this really noisy room. Can't make much sense out of it. So everyone knows you got to do something, but what? So you start running some solutions up the flagpole, and you start having discussions again. Right? People start talking about the merits of solution A versus solution B, and you start to miss the point. Right? You run a really big solution up the flagpole, and everyone, it's too radical. You can't do that. You try and do something small, and people are angry because it doesn't do enough. So, what do we do? And the problem is, what we wind up doing is having a discussion that looks something like this. Right? Oh, but C# can do blank. Why can't I have unsafe? So, not useful. So we got to take a step back here, and we got to try and figure out what the really fundamental building blocks we can use for tackling categories of solutions, to use John's term, and not let the labels and the particular merits and use cases get in the way of figuring out, what the core atoms are. So I'm going to take a little bit of walk down memory lane here and look at some of the places that got us to where we are. And unfortunately, John really stole my thunder with this slide, because his Sumerian thing was way cooler than this. But back in the good old days, data, you chiseled it on a tablet. Really great security in one of these things. It's really hard to change. It's really hard to steal. Anyways, it's a joke slide, but the reality is that organizing data is basically the fundamental thing in technology and science. It's what's gotten us to where we are today, right? The Dewey Decimal System is structured data. It's hugely important. Right, so modern day, early computers. Well, punch cards, mag tape, these were all about serial access. I mean, you could emulate random access if you really, really wanted to, but it just wasn't worth it. So data structure here is not a metaphor. It's how it's laid out. When you're reading things off the tape, then the order they are in the tape is your data structure. But on the plus side, it's really simple. It's easy to understand. I mean, Turing picked this for a reason. Right, so that was the hardware of the day. What about the software of the day? FORTRAN is the first stop. Really the first big high-level language. And it was just meant to be an easy way to write assembly code. I mean, machine code was hard. Machines kept changing. Wouldn't it be great if we had a way to express these things? And it was basically a direct map onto the hardware, right? Here's your primitive types. They look like the hardware registers. You got a few little niceties like complex, but you really couldn't design your own types. And, mutability, what's that? Your data comes in off the card and goes out to the line printer. The heck is mutability? All right, so completely different. We've got our friend COBOL. So here we have portability as a concern. And I mean, this is a radical idea. At the time, we didn't even know how many bits were in a byte. And instead, we have this notion of let's have a portable language. And unfortunately, that meant it was designed by a committee, and we know how that way goes. But for the first time, we really had this notion of sort of composite data types. And we did this by starting out with cells. You said, how many cells do you want, right? If you wanted a string, you said how many characters you wanted. If you wanted a number, you said how many digits you wanted. And you could chain these things together. Right? And you could have a type that was composed of other types. So great, we've got this composite data type for the first time. It doesn't look anything like the hardware. Clearly, your performance is not going to be great. But if you want to write this thing to a database, hey, it's a match made in heaven. And that's not a coincidence, because the same committee that was designing COBOL was in the next room designing relational databases. So we got a couple of languages here that were really good for solving two very different classes of problems that were very popular at the time, right? FORTRAN is great for doing computation, and it's still out there. It's still doing computation. I mean, it's evolved past a lot of these little limitations here, but it's still out there. Still good stuff. COBOL less so. I shouldn't say that as an IBM guy, but there you go. It was great at managing data. It was great at reports. What if you wanted to write some code? Well, Lisp. Everyone likes Lisp, right? Lisp was not about the data. It was all about the code. If you wanted to have a data structure, then you wrote code that manipulated the data. You had a couple of primitive types, but really you just had one type. You got the const cell. Everyone knows what it looks like. Nobody looks at it. It was completely abstract. And this was an exciting new thing because it meant that the runtime had all kinds of scary new powers. You know, GC is a direct outgrowth of this. So, of course, there's always a cost here. Abstraction always takes away performance. And this data's not flat anymore. You don't know what it's laid out like. And you know what? It didn't matter. It really didn't. So, things have changed since those days. Let's look at some of the really hot button topics these days. Security. Try not to leave the keys in the machine. Concurrency. Buy 2 boxes. Or is this really parallelism? Does it really matter? Mobile computing. Good stuff. First portable computer. Well, more portable than a stone tablet, but, you know. Networking. I love this slide. So this is a complete diagram of the ARPANET from '77. So it's a great example, you know, when you're trying to design tomorrow's solution, you look at a problem like this and you say, okay, we got a couple of hundred machines, tops. We need the next generation thing. Should we give ourselves an order of magnitude? Should we give ourselves 2? No, they went for a full 32-bit address space. I mean, that's a millionfold what we got on screen here. Really, they were thinking ahead. Unfortunately, it turns out they didn't think far enough ahead. All right, so let's talk software again. The big beast, C. I mean, let's face it, it's the de facto standard for doing blank on blank. And the reason for that is the world needed a portable language. Hardware kept changing. There were so many vendors, so many architectures, they kept iterating. The world needed something where you could kind of trust it. And it's really a bit of a mishmash, right? You got the FORTRAN hardware types. You've got the composite COBOL types. You've got those great pointer structures you could build in Lisp, except suddenly, those pointers are for you. That was a whole new way of doing things. And unfortunately, it also meant that we had a whole new class of bugs. You've got all this great expressive power you never had before, and it turned out to be really good for shooting yourself in the foot. I mean, previously, if you wanted to write a memory leak, you probably had to be writing assembly code. Now everyone can do it. It's the great democratizer, right? So, you know, it slices, it dices. It's the Swiss Army chainsaw. I one-up John here with the knife slide. This is an actual thing. You can buy this. I think ThinkGeek has them. I wonder what it weighs, but Anyways, so C is this great language you can use to do absolutely anything. And I mean, it's kept up with the demands. You know, volatile got added, buffer overrun stuff, reentrant libraries, we added on P threads. You can just keep warding stuff onto C and it can take it. You know, does it make it the right tool for a job? No, it's almost always the wrong tool, but you can always get the job done in C. Of course, you can always ruin yourself in C too. I mean, all these things we care about. Security, whatever, the OS will keep you safe, right? You want threading or processing, just add on a library, call the OS, whatever. Immutability, yeah, sure you can declare something const, but you can work around that. Right, so here's the other big one. Unfortunately, it's not one that ever really caught on, but man, it's had a lot of influence and continues to today. So again, we have the Lisp-style idea of, let's give you a language where you can write a lot of code, you can get a lot done, and it's really hard to hurt yourself. The downside of that is, once the world had seen C, this living in a nice, safe little box was just too limiting. People needed to talk to the outside world, and really, Smalltalk didn't give you a good way to do that. I mean, every vendor always had a back door, but nobody wanted to learn it. I mean, I cut my teeth on Envy Smalltalk, and we had, I think there was one file that was part README and part example for how to write your own primitives. And if you weren't on the VM team, you probably weren't going to understand the README file. And if you were, you didn't need the README file. But, you know, once again here, we have the sort of abstract, non-flat data that gets a lot done. So, where are we in the world? Well, I tried to get a slide where I could put the whole internet back up there, and it doesn't really work. I mean, there's a little zoom-in box there, but it kind of needs a zoom-in box on top of that. And this picture's like 9 years old. So, you know, that 32-bit address space, it ran out years ago. We've been working around it, but it's a problem we got to solve. But suddenly, network connectivity is not some novelty. It's a necessity. It's always on. And unfortunately, when your network is always on, that means your security had better be always on. Right? If you can talk to something, you can try and subvert it. If you can't subvert it, well, you just drown it. And if you can't do that, well, you can always post nasty things on Twitter, right? How about the hardware? So, everyone's favorite model, right? You got a processor, you got some memory, you got disks. You run into memory, you swap it to disk. It's easy, right? You keep your working set small, it just works. Then we get cache. Free speed, right? Who doesn't like free speed? Multi-layer cache, more free speed. Unfortunately, it's free speed because main memory just wasn't keeping up. We really needed these extra layers. And now things start to get hard. You know, you need bus locks, you've got Snoopy caches, suddenly concurrent modification is a thing you got to think about. But, you know, to be honest, if you just run 2 processes on this instead of 1, it's just going to work. If you really want them both, just run 2 different threads. As long as they're not competing for the same data, you're good, right? SMT. It's just more of the same, right? We can keep those busy. It's no worries, right? All right. This is closing in on where we are today, and it's not so easy anymore, right? How do we keep all these processors busy? And meanwhile, those chip designers, those sneaky guys, they're starting to do things like weak memory ordering. It's just getting harder and harder. How do we deal with this? Well, let's not deal with it. And this is how we got by, right? We said, okay, well, this isn't just 1 machine, this is 8 machines. Let's virtualize it and go back to the good old easy days where we didn't have to worry about this stuff. And somebody will solve this problem later, right? That's coming, right? And here's where we are today. And I guess we could use a lot of virtualization, right? But really, are we using the power of the hardware anymore? You know, it's sort of fallen apart. And, you know, you look to the horizon, and now you've got this. And this is going to be really important, but we can't virtualize our way out of this. We really need a different way of looking at things. So, move on to Mr. Rose.
Thank you. I think I just coined a new acronym, NUPA, Non-Uniform Processing Architecture. Isn't that where we're heading? NUMA and NUPA together. So to extend the historical review, we come to Java as a nice resting place that virtualizes some of the details that were on those disturbing previous slides. But of course, as I pointed out earlier, the JVM is, part of the job of the JVM is to align with the hardware and expose its natural abilities, which means exposing, to some degree, the numinous and certainly the parallelism that's inherent in those big, scary devices that were summarized on the previous slide. Java, of course, was initially created for very small devices, set-top boxes, as some of you may remember, and it just so happened to be categorically designed, or at least well enough designed, to apply to a wide range of computing devices, and amazingly, today it even applies to massive multi-core servers. But we don't take this for granted, and so we have to continue looking at how to evolve our platform to catch up with the hardware, even as the hardware is trying to catch up with the code loads that we're sending at it. So in any case, here we are with a managed runtime and a virtualized instruction architecture, which gives us at least a foothold in this crazy race between ever more complex software and hardware. We are familiar with Java, of course, in this room, but I want to briefly review a small number of the buzzwords that go with Java. It is a virtual machine that is, as I just said, close enough to the hardware, but it's not so close to the hardware that you can saw your foot off with that big, scary knife. You have a certain amount of security in your code loading and your access control, so you can make secure encapsulations. You can load at least partially untrusted code into your system if you wish, and so it's more like Lisp in the sense that it's hard to crash. Another thing about Java that was very forward-looking back in the day, and now it's something we've just all gotten used to, is the support for managed data with not only encapsulation but guaranteed integrity, so that even if someone tries to break it, it's supposed to be hard to break. Supposed to, because I have some scars from various critical patch update adventures and security reports and so forth. But did someone say something about security? I'm going to stop talking about it now because it's a painful subject. And yet we think we're somewhat successful in fending off the attacks. One thing that's happy about Java, it's not just that it avoids attacks, but it's actually friendly to threads, which again, like GC, was forward-thinking back in the day, and now it's just absolutely can't live without it. Upstairs in the Sumatra room, we were just talking about how to take Java's concurrent model, which expresses parallelism very well up to fork join, and sort of refine it down so that parallelism can be pushed onto the GPU, and that's the exciting work of Sumatra. So amazingly, Java can be even wedged onto a GPU, but it's going to require long-term adjustments to the JMM and threading models to get there. One funny thing about Java, of course, and just to remind us all, because this plays into value types and flat data, is classic Java had just enough non-object types to make people laugh at it who were purely object-oriented in their mindset, like the small talk people. So you had the 8 primitive types and then all the array types, which is a brilliantly practical move, but it, as we've seen in other talks, needs some updating today. A final bit that I want to remind us about Java is from the very beginning, it had a fairly clean interconnect with native code. It was Java-centric in the sense that your native methods that you could call had to be preconditioned to be callable from Java, and they had to obey all sorts of fancy system invariants and use special macros and header files and so forth. But once within those native functions, you could do a fair amount of native type work before going back to Java. And of course, this was necessary in part just to implement the virtual machine itself, functions like wait or something like that, or the I/O functions. But also, in order to, this was maybe one of the earliest multi-language moves that Java made, in order to make it useful to other people who wanted to write their own native methods, JNI was standardized fairly accurately, in a detailed, usable way, so that how many of you out there have written a JNI native method? Right. Now raise your hand if you are an implementer of a JVM. Okay, so I would say 1/3 of the people that raised their hands the first time did not raise their hands the second time. So that means that there's a fair number of non-JVM implementers using JNI, but the majority, in this room at least, are the JVM implementers. Okay, well that spoils my point partially, but I'm going to roll on. So the native interconnect is my jumping off point to talk about flat data. The JNI is the current way that you talk to C data structures via C functions. And so naturally, as a wise man said, the solutions of today are the problems of tomorrow. So JNI has become the problem of yesterday's tomorrow, which is today, if you follow me. So it is a quite cool thing. I'm not going to diss it. We wouldn't be here without it. It's one of the distinctives of our platform. It gives the VM a lot of freedom to be the VM and still let C do its job through brilliant use of handles and virtualized interfaces and not quite pinning operations. There's no point at which there is a native pointer exposed to a JNI function, which is really a remarkable achievement if you look at the way native interfaces are done in other languages, such as Python or R, where it's a hard problem to disentangle the VM if you want to re-implement it from the native functions that have been attached to it, like barnacles feasting upon the rotting side of a ship. Okay. Preserving the freedom of the JVM. The problem with JNI is that it's useful, it's necessary, and as we saw, some non-VM people have used it, and it's become a catch-all for code that couldn't fit in Java. The problem with that is it's kind of expensive. It goes through multiple levels of indirection in order to provide abstraction, and so you have to use it with great care in order to preserve performance. In fact, it's kind of a black art doing performant JNI. You have to sort of move all the loops to one side or the other. You can't have a loop that crosses JNI boundaries. There's another alternative. You can always jump in the unsafe water, and there you no longer have a nice box for your VM and a nice box for your native code. You're mixing it all up. How many of you have written code that uses the Unsafe API? Wow, as many as have done JNI, pretty much. That's remarkable. Gosh, I'm sorry. Wow, yeah. So, you know, in the old days of Lisp, where it wasn't as secure as Java, it was intended to be abstract, but you were supposed to be able to have, when you needed it, access to the low-level junk. Some Lisp platforms used a little % or some other scary-looking accidental character to mark the identifiers that were unsafe. And so those of us who did the same thing with Lisp would use, you know, % pointer ref or operations like that would take an integer and get the byte that was at that address. All that kind of peek and poke type stuff. You could do it in Lisp, right? You can probably do it in other managed languages today if you attach to the right package. Well, Unsafe is that for Java. So that way of doing things invaded Java just enough to make things interesting. One thing that's, by the way, that's nice about Java is the packages have a certain amount of access control on them, right? So it's actually possible to say, this package is for super users only, and you have to do something conscious to turn it on. And if you're running in restricted mode, then you can't reach it. We have reasonable proofs that people can't reach Unsafe, at least under any normal conditions, if the restricted access mode is turned on. The reasonable proofs involve having, you know, Tiger teams attack it. So, well, what could be better than that? How about easier, safer, faster, all at once? Pick 3 out of 3. We're hopeful, aren't we, Charlie? Yes, we are hopeful. So what we think we can get to, and it's time to design this and to work on top of excellent designs that are out there right now, is a foreign function interface which is flexible to use. Say it doesn't require you to write specially preconditioned C functions, which we're all used to doing, right? But wouldn't it be nice if you could just call printf when you meant printf, and, you know, worry about the JVM safety interlocks and have somebody well, maybe printf's inherently unsafe, isn't it? Yes. Something else than printf. If you can think of a C function that's safe, let me know. I think getPid is one. In any case, mixing languages is difficult, as you probably noticed from my blog on the isthmus and the VM. The blog entry spends much of its time talking about how the safety expectations are different in the Java and C camps, which definitely we have to take into account. But given some reasonable rules about using C, and they exist, JNI is an existence proof of that, given those rules, we can flexibly implement them by wrapper spinning rather than by forcing legions of C coders to code JNI wrapper functions. That's my contention about easy FFI. And JNR is an intriguing indication that that's true. Okay, what else can we do to make native code and data access? Well, the other things that we've been talking about, new arrays and value types. The new arrays are not just for Java heap. The array APIs should be polymorphic, will be polymorphic enough to talk about off-heap data as well as on-heap, and maybe within the same type both. That's optimal. Value types, of course, are a useful new blade in the Swiss Army knife, and they will let us talk directly about the kind of flattened data structure that you find in native data. And let's be frank, when we as JVM people talk about flattened data structure, what we're really saying is that we like managed pointers, but we don't like them on all of our meals, and we're going to have a plate here of bits with no managed pointers in them. That's what flat data structure means for us. It might also, for a C programmer, mean, and yeah, the things are collocated, and there's fewer C pointers in the middle of it too, and that's nice. But primarily, when we talk about flat data structure, that means something that doesn't have all these managed pointers that have to be treated specially. So value types, the ones that don't contain the managed pointers, will very naturally be something that you'll be pushing and pulling into native storage. So the thing that's a little bit new, it's been referred to earlier, is the idea of smart foreign pointers. And I want to go through some of the details of that. And in this, I'm following sort of an average path between a prototype that IBM has done, the J9 group. It's in the J9 group, isn't it? That IBM has done, and a prototype that Oracle has done. The person at Oracle, his name is David Chase. I wish he could be here. He should be talking instead of me. But he has some prototype code for what I'm about to show you that's posted right now on the Sumatra repo, but it's going to be brought into the Panama repo. So smart foreign pointers. A foreign pointer is for a managed runtime or a language that thinks it's the only natural language, like Smalltalk or Lisp or Java. A foreign pointer is what those guys do over there in that land that's not quite civilized. A foreign pointer is, yeah, we can use pejoratives, can't we? A foreign pointer is one which has some ability to have correctness and management and class structure. It's a classy pointer, but it sort of walks on the wild side. It's classy in the sense that in Java, it will have methods on it. It will have types, strong types, Java types. It will have appropriate null checks and all the amenities of home. But when you reach through it, you'll be reaching off heap into some C data structure. And the rules for reaching into the C data structure might involve pull out a bit field using shift and extract, right? There might be some funny rules there. The rules also might include, well, C does its arrays or FORTRAN does its arrays differently than Java does, and so if I'm going to pick the third array out, then maybe I got to use special rules for reaching over there. So a foreign pointer will encapsulate all the type-specific knowledge of the layout on the C side and bring it back into a programmable handle on the Java side. Let me show you some structure. Foreign pointer, I contend, is naturally composed of an address expression, which is at least a virtual address, plus a little bit of type and maybe scope information. The scope information would be something that would be used with handshakes to safely work with memory arenas that are not infinitely long-lived, which is not a topic. You can ask me about that. And I think there was somebody put up the scoped memory construct already, so we'll just leave it at that on an earlier talk. But the base object goes with the address. It's part of the addressing mode, and practically everybody in this room is already coded with Unsafe, so you already know what the base adder and the base object and the long address do. They add together, and then that gives you both on-heap and off-heap access. And then there's also a layout object. Now, this smart pointer, his name is location, and he contains, as one of his fields, a layout. The layout is an immutable piece of metadata that says all the details about how to get and set values and what's in there and in the neighborhood of that value. And the address and the base object are of course untyped and dangerous to use by themselves. So the smart pointer will have encapsulation around these things. There'll be a factory for smart pointers which will be trusted and will create only ones that are trustworthy, the right metadata with the right addresses. Here's how a dereference looks. Now smart pointers do not have virtual methods on them. They just have statically bound methods on them. So when you pull the value out of a smart pointer, a location object, you ask its layout to do that for you. And you pass in the address components. And likewise with put. The current prototype of this, not very surprisingly, expresses these locations or these smart pointer objects as value-based classes. In the sense that they're all final, you don't synchronize on them. There's nothing objecty about their usage, and so they ought to be, and someday will be, value types, little groups of 3 or 4 registers. There's on the slide, which you will be able to find online afterwards, is a long link to the file that has this stuff for those who are curious in the Sumatra repo, and this is a thing that's going to be in Panama in an updated form. So what's the layout? Now, a layout is the abstract shape of a location. many locations can have one layout. So that's the object entity relation, right? Layout is metadata, location is data. A layout has obviously some size and alignment attributes. It also has some kind of a representation of at least the Java view of the class of the object that you're going to get in the set inside of it, and that would often be a value type, like complex or something. These days, it's, we're parameterizing over references, because that's all we can do. There's an abstract value which is implemented. As you saw before, how the val call is, you say p.val, it goes to layout.val. This thing is abstract because, okay, somebody's got to write a subtype, a subclass of this. That's the job of a trusted factory system that builds wrapper classes, and we'll use all of our wrapper spinning foo to keep that stuff working properly. What sorts of layouts are there? Well, what sorts of data are you interested in? Do you want arrays? Do you want structs? Do you want integers of what width? 128 bits, 256 bits, 4 bits? You want 4-bit column major matrices? Can do it. It's all composable. The prototype actually does that stuff. David is amazingly thorough. The interesting thing is we're not claiming that one metadata system can express the one true foreign array type. We recognize that there are C arrays and FORTRAN arrays and R arrays and probably protocol buffer arrays and thrift arrays, and they all have their own rules for layout. And so we expect that there'll be different drivers, plugins, to create different kinds of metadata for the different data structures that we want to get to. So you remember, going back to the beginning of this talk, Karl's colored balloons of people wanting different parts of the elephant. This guy wants the tail, and this guy wants the left foreleg, and this guy wants the trunk. You know, the blind man and the elephant. That's the we live there a lot in this JVM design world. Well, it turns out that we can supply all of those things if we have the right pluggability in our metadata protocol. In fact, this is very much like the old-fashioned idea of a meta-object protocol. Hello, Attila. We need a new protocol. It's the metadata protocol now. Yeah, so that's clearly what we'll be building in order to have all sorts of different data layouts be available to us. Okay, moving on. What's it got to do with flatness? Well, the linkage to flatness and nativeness, besides what I already said, is that if you want data structures which not only squeeze out squeeze out the managed pointers and the object headers, so they're clean of that stuff. They don't have heaps, Java heap stuff in them, but they also have some other clever optimized format. And you know, most of us have probably written data structures where we had to count the bytes and be sure that we didn't have too many slop words in there, and we used a bit mask instead of a null pointer to declare optionality of some parts and so forth. That whole exercise eventually creates its own little language, its own little data language of your favorite kind of data structure. I know I have mine, at least. And Avro is an example I like to look at, even though I know it's not so widely used, but it's got a cute set of design aesthetics all mixed in for creating a certain kind of compact data. Why is this related to the stuff I've been talking about before? Because in order to represent data that is compact and or native, you need a large number of degrees of freedom in your layout calculus, in your metadata protocol. So you need these abstract smart pointers that are parameterized by extremely variable type information. Yeah, that's probably enough on that point. And I've already talked a little bit about where the metadata comes from, but there really are, you just keep pulling on the string and you keep thinking of more places you can get metadata from. What are IDL files? Well, they're specifications of some sort of protocol or data structure, bulk data structure layout, and they're supposed to be compiled to somebody's access function, but we think they should be compiled to layout generators, layout factories, so that we can point our foreign pointers at whatever that weirdo IDL format is and pull data out of it. We, of course, need tools, or at least good working practices for creating these factories. We don't want them to be all written by hand. There is a special need for a C++ header file parser. Very luckily for everyone in this room today, libclang is an excellent C++ front end, reasonably up to date, and used in production. We should be libclanging the APIs that we need from C to be pulled into the metadata engine. And there's prototypes of that even. It's very cool. A few more notes about why flat's good. And this is hardware oriented. I think we are getting back to Turing machines, or at least towards Donald Knuth's style art of computer programming mag tape algorithms. Memory is sequential under the hood. Memory likes to be fetched in order by cache line by cache line. Within a cache line, okay, you can random access the first or the last word, fine. But the cache lines as a whole like to stream at you in some order that the prefetcher can predict. And that usually means some kind of linear sequence, probably contiguous. So that's the hardware reason why flat is important. The hardware wants to serve you your data by flat slabs on roughly the kilobyte scale. That's why hardware, when people expose that stuff to software folks, we see abstractions like streams or vector iteration spaces, array iteration spaces. And this is due to a very complicated interrelated conversation between the hardware and the software people, but it looks like the software people, even though they believe they're doing random access, the hardware says, I see you're doing that sequential thing again, I know how to get that for you in time. We probably are doing sequential access more than we think. In any case, I do believe that as memory scales bigger and bigger and it gets farther and farther away from processing, it will become more and more important to use sequential forms of access and not be all random and CASI with the hardware. GC helps. GC, if on a very good day, GC will reorganize your data structure into some sort of quasi-depth first order and make it perfect to stream over the next time. On a really good day. On most other days, it'll reverse the order, and the prefetcher will absolutely fail after your minor GC after data promotion. The prefetcher won't be able to find your data in order anymore. I see GC people smiling at me. Yes, I see that too. Okay, so Java is in conflict with big data. Java is, after all, from set-top boxes. Let's fix that. 64-bit indexes, please, for our collections. Zero-copy algorithms, please. And by the way, this is scale matters. I'm not talking about contiguous or flat terabytes. I'm talking about contiguous or flat kilobytes. Very important to keep in mind that different scales have different rules. Concurrency management, very briefly. What are the tactics? I think it's important to realize that when you work with arrays or flat data in general, that the arrays have a life cycle. They have a life cycle where they're being initialized, and they have a life cycle when they're being read, and you get race conditions if you don't adequately distinguish between those portions of the life cycle. And so I believe, this is just me thinking out loud, but for what it's worth, that there's a small number of discrete incompatible tactics that you should be using with array data one at a time, and switching with fences, strong fencing of some sort when you change tactics, and that involves read-only, write-only, and some sort of confined update. Future hardware might help us with this, but I think it's going to get more sequential. Okay, I already talked about that. Array APIs, by the way, if they're just element-wise, they lose. Imagine trying to program in APL, but you can only access one element at a time. How much fun would that be? Well, that's what the square bracket notation does for us in Java. So we're not there yet with our array notations. Java itself sometimes conflicts with itself because we have such a wonderful user base of about 10 million programmers, no joke, that we have enormous momentum to keep doing what we're doing. So we have this fun intellectual exercise of being compatible with the past while embracing the future. And the future is stretching us as the hardware carries us off in some directions, and the language theorists sometimes pull us in other directions. A couple of very brief notes. Let's not reinvent the register keyword. Let's not have today's quick fix be tomorrow's cancer. Where are we going? Well, it's time to investigate, and we have the OpenJDK as a wonderful large-scale playground for investigating, including Project Panama, as has already been described, and also Project Valhalla. So let's keep thinking. Let's keep exploring use cases. Let's make it powerful and keep it safe out there. Yeah, we're going to make this stuff happen. Questions? Right. So the question is, why don't all languages have Java's int, char, short? All right. Given that they're going to be foreign over there, how are we going to cope with it? I don't think I'm being too Pollyannish by saying value types will help with that too. You can make an unsigned value type, which will be exactly 32 bits. And will contain in it, as far as the method is concerned, a signed Java int, but we'll never expose that sign.
But if you want to treat it like it, you have to remember that it's unsigned and passing the array and all this stuff. Whereas if it's signed, you can just use plus.
Right, yeah, okay. So thank you, right. Yeah, so yeah, the signed in native normal natural Java ints do get the benefits of plus, minus, times, and divide, whereas the value types do not. We are not planning operator overloading. Yeah, that's a problem.
That's sort of the easy form, but the thing we spend a lot of CPU cycles doing is just converting back and forth between UTF-8 and UTF-16. A lot of the time we don't have to.
Oh yeah, UTF-8 and 16, right. That's an ongoing quest. Zero copy is a win, by the way, in case nobody said it. But yeah.
I think the problem with this is value classes are great. Like, we'll have great value classes, and we have intrinsics for like unsigned divides now and things like that. As soon as you get to like, I want to do 128 in math or something else like that, you still need to extend the VM to have the intrinsics. Otherwise, you're going to be doing long division in Java code. That's
Right, okay, so the observation is if you want to do 128-bit multiplier divide, then the options seem to be limited. There are at least two options. One is you make a native method, and the other is you use schoolbook algorithm. But the secret option with schoolbook algorithm is you can have the JIT, you can have the VM intrinsify it anyway, if it likes. So you can use this, you can get both at the same time. Yeah, well, in the end, you want the VM to be able to code generate all of the instructions of the platform. Exactly. Yes. Well, value types are an exercise in enhancing the scalar types of Java so that we can begin to express those calculations, maybe with syntax that we don't quite like, but at least we can express it, which is a huge step forward. And then if the JVM can generate those instructions, it'll be obvious where to find the methods that utter them, even if they're schoolbook algorithm methods.
What Dane is saying is basically if we don't provide a pluggable mechanism for him to intrinsify anything he wants, then we've done nothing, right? No, seriously, you're looking like 9 steps ahead. We're planning 5 steps ahead.
I totally agree. And I think it's an awesome way to, along the road, I'm saying like there are additional things that are going to be required to make things like big math or make complex numbers work efficiently on CPUs. You have to do what's efficient on CPU.
Aren't you planning to retire after JDK 10? I thought we'd all be done by that point.